Good afternoon, students. Today we are in the continuity of the topic vibrations. In that, it is a transverse vibrations. In the last class, we have discussed about the content related to what is vibration, types of vibrations, that is free, force, or damped. Under free vibrations, what are the types? That is longitudinal, transverse, and a torsional. So, in the last class, we have found the equation for natural frequency under of free longitudinal vibrations. In the today's class, we will go for natural frequency of the free transverse vibrations. So, the transverse vibrations means the body or the vibration is created approximately perpendicular. So, in this case, the transverse vibrations will be creation for that. Consider a shaft of negligible mass whose one end is fixed and the other end is carrying a weight of W. If you see in the diagram here, let S be the stiffness of the shaft and delta with the static deflection due to weight. So the deflection means change in the displacement, and x is the displacement of the body from mean position after time t. How much of distance it was traveled. M is equals to mass of the body, that is weight is equals to mg. Based on that, W is equals to mg. Here we are calculating the mass with m is equals to W by g. We know that the restoring force that we have discussed in the free longitudinal vibrations, the restoring force and restoring couple, that the restoring force is equals to minus Sx, and the accelerating force is equals to m into d square x by dt square. These things we discussed uh, in the previous class, that is free longitudinal vibrations. If you equate these two, ma d square x by dt square is equals to minus Sx, or m d square x by dt square plus Sx is equals to 0. The both are same. By dividing and multiplying with the m on both sides, it is d square x by dt square into s by m into x equal to 0. Here the time period and the natural frequency of the transverse vibration is also same as that of the longitudinal vibration. The formulas are both are same. So time period is equals to 2 pi into square root of m by s, and the reciprocal of the time period is natural frequency. So Fn is equals to 1 by Tp, that is 1 by 2 pi into square root of S by m. Simply S by n is equals to, we can straight away we write it as square root of g by delta. So g by delta is equals to S by m. The deflection, here the mainly is the deflection. So in this, the frequency is mainly depending on the delta only, since 2 pi is constant, g is also constant. And what is the delta? Only the main element of deflection. The delta is the deflection, means this is different for the designs. That is, the curved shapes, if you let us consider a curved shape which is vibrating, that will deflect is identical with the static deflection curve of cantilever beam which is loaded at the end. So the deflection of the cantilever beam which is loaded at the free end, the formula is how much? That we already you can discuss in the strength of materials, that is delta is equals to WL cube by 3EI, that is cantilever beam deflection. During bending moment diagram, shear force diagram, we are calculating these deflections. So W delta is equals to WL cube by 3A. This is the main formula we need to remember for formulating or calculating the deflection. So let us consider a problem on this. A cantilever beam which is 50 mm dia and 300 mm long has a disk of mass 100 kg at its free end. So here we are considering a cantilever shaft 50 mm dia and 300 mm long length. One end is fixed and the another end is freed, and the free end is weighing a mass of 100 kg, and the Young's modulus E, that is material property, that is E is equals to 200 giganewton per meters square. Determine the frequency of longitudinal transverse vibration of the shaft. So what is the formulas mainly here? Longitudinal and transverse vibrations. Both the formulas are same. What is that? 1 by 2 pi into square root of g by delta. That is the frequency formula. And then one more thing is there, by simplifying the formula, natural frequency Fn is equals to 0.4985 by root delta. So the above all the 1 by 2 pi into square root of g, these are all numerical values. Those are constant values. Those are all coming to a single value called 0.4985 by root of delta. So now the problem is simply calculating the delta is enough for calculating the natural frequency. Then what is the delta deflection of cantilever? Shaft is the main thing. So for and at the same time for longitudinal and transverse vibration, the formulas may be the differ. So the delta formula for the beam which is under longitudinal vibration or static deflection is WL by AE. For transverse, just now we thought that WL cube by 3EI. That is just now we explained about this deflection formula. So by substituting these, given data as D is equals to 50 mm and L is equals to 300 mm, so we can convert these to meters, since there the Young's modulus is in the notation of meters, and M is equals to 100 kg, E is equals to 200 giganewton per meter square. Giga means 10 to the power of 9. So find out the longitudinal vibrations. For longitudinal vibration, what is the deflection formula? Delta is equals to WL by AE. We know the value of W. Since mass into W is equals to M into G. M we know 100, G we know 9.81. By substituting that, we can directly calculate. There, one more thing is A and E, WL by AE, that is the formula. W in the from the given data, L is also from the given data, E already given. Whatever the next thing, A you need to find out. A means area of the shaft. So A is the area of the shaft, whether it is a hollow shaft or a solid shaft. That is cross-sectional area of the shaft, pi by 4 d square. So pi by 4, A is equals to pi by 4 d square, d already given, pi by 4 into 0.05. Already we explained about the units conversion, that is not be in mm, it always be in meters. After converting pi by 4 into 0.05 whole square, 1.96 into 10 to the power of minus 3 meters square. Then this is value is enough to substitute. So delta is equals to WL by AE. W is 100 into 9.81. L is equals to 0.3 by A. How much of value? 1.96 into 10 to the power of minus 3 into E is 200 into 10 to the power of 9. By calculating this, we get 0.751 into 10 to the power of minus 6. Then what is the formula for frequency? For longitudinal or transverse, for both is same. Fn is equals to 0.4985 by square root of delta. So 0.4985 by root delta. Root of delta is 0.751 into 10 to the power of minus 6. So finally we got the frequency as 575 Hz. Then next, frequency of transverse vibration. We know that the transverse vibration formula is same, both the same, but the deflection formula is delta is equals to WL by 3EI. So W we know, L we know, E we know. Whatever the I is called the moment of inertia of the shaft. So whatever the moment of inertia formula, I is equals to pi by 64 into d power 4. Pi by 64 into d power 4. So substitute them. From this, I is equals to 0.3 into 10 to the power of minus 6. So by substituting that, we got delta as 0.147 into 10 to the power of minus 3. So 0.4985 by square root of 0.147 into 10 to the power of minus 3 equal to 41 Hz. This is the formula we received, or finally the value what we received in the finally. So in the these type of simple manner, the problems will be asked in the examination. Then finally, the natural frequency of the free transverse vibration due to at a point acting over a simply supported shaft. Let us consider the diagram. If you see in the diagram, let us consider a shaft AB which is of length L. So the diagram AE is the shaft and which is of length L, which is carrying a load W at C. The C position is at a distance of L1 and L2, which are all from A and E. If you see in the diagram, the load is acting at the C point, the load is W, but the carrying load is applied at the C position, which is at a length L1 and L2 from A and E respectively. A little consideration is taken into account when the shaft is deflected and suddenly released. So, with the application of the load, the shaft will come down, and when we released, there is a deflection and it makes some transverse vibration. The deflection is directly proportional to applying weight or applying load W, and if the beam is deflected beyond the static position, then the load will vibrate with simple harmonic motion. So here we are applying as a simple harmonic motion. There the static deflection delta, which is due to the load, so that the frequency formula, as we all of you know, that is Fn is equals to 1 by 2 pi into square root of G by delta, simply 0.4985 by square root of delta. But here, for some of the values of static deflection for the various types of beams under various conditions, we are, for remembering these, we are taking into the account. So one is cantilever beam with a point load W at the free end. Here it is a cantilever beam with point load at the free end. So what is the deflection? Delta is equals to WL cube by 3EI. That is a formula. And cantilever beam with UDL, that is uniformly distributed load. Uniformly distributed load of W. Then the formula is delta is equals to WL to the power of 4 by 8 EI at the free end only. Then the third one is simply supported beam with an eccentric load. So that is called, we call it as a point load. So if you see in the diagram, third diagram, simply supported beam, but the weight is applying at a certain distance from the two ends. One is from A and another is B. There the deflection is delta is equals to W L to the power of 4, that is L means total end, but the load is acting at certain position, that is A square B square by 3EIL at the point load. Then simply supported beam with UDL. Formula for UDL in the previous slide, formula for UDL, that is WL to the power of 4 by 8 EI. Here also the UDLA, but that is cantilever, this is simply supported. This 4 WL to the power of 4 by EI into 5 by 384. Then fixed beam with an eccentric point load W. That is W fixed beam, previously simply supported beam. Delta is equals to W into A cube B cube by 3EIL. Next, fixed beam with a central point load. That is eccentric load. This is central load. So W L cube by 192 EI. Next, simply supported beam with a central load W. W delta is equal to WL cube by 8 EI. Next, fixed beam with UDL. Delta is equals to WL to the power of 4 by 384 EI. So these are the 8 varieties of beams. Accordingly, the deflections also we have noted. Then coming to the problem. A shaft of length 0.75 meters which is supported freely at the ends, which is carrying a body of mass 90 kg at 0.25 meters from one end. Find the natural frequency of transverse vibration assuming E is equals to 200 giganewton per meter square and shaft dia is 50 mm. So firstly we have to write up the given data. Given L is equals to 0.75 M 90 and E is equals to 200 into 10 to the power of 9 Newton per meter square. Dia D is equals to 50 mm. What we are asking here is find the frequency. We know that formula is 0.4985 by square root of delta. Here the main problem is for transverse vibration only. The thing is for calculating the moment of inertia. Since it is a freely at the ends, the end is freed, but the carrying load at a from one end it is 0.25 distance with a load 90 kg. So in the diagram, if you see in the diagram, that is a free, no fixed, no UDL, only a freely supported, not and 90 kg is applied at 0.25 from A. Actually, in this diagram, we can alternatively take up one more diagram as from B, we can choose 0.25. It is also a correct. Since in the question, they have not mentioned clearly from A or from left side end or from right side end like that, they won't mention the details. So here we can take up the one end as either A or B. So both will be the correct one. Then for this condition, delta value, the static deflection at the point load for freely. For freely, what is the formula? Already we discussed so many of variety of products. So if you go there, simply supported, so this is called simply supported, the weight at the center. So here case, the simply supported at a certain distance from the, so actually the length is 0.75 meters. In the question, if you see in the length as 0.75, half of the length, that is 0.375. But where the load is applied, center means 0.375. The load is applied at 0.25. So it is a point load which is not at the center. So this formula is incorrect. Simply supported UDL, no UDL. So here also wrong. Cantilever, one end is fixed, no other end is fixed. 2. If you see the diagram 3, simply supported beam with eccentric point load. That is, this formula will be the correct one. This is only the one. So delta is equals to W A square B square by 3EIL. This is the formula we have learned. A means from left side and B means from the remaining one or right side end. So if you substitute delta as W A square B square by 3EIL. W we know 19. A means W means M into G. So M is 90. G means 9.81. 9.81 into A square. A means from the left end, that is A, from the right end, that is B. So 0.25 square into 0.5 square by 3E 200 into 10 to the power of 9 I into L. L is 0.75. What about the I? What is the formula for I? For solid bodies, solid shaft, I is moment of inertia, that is pi by 64 into d power 4. So d power 4 is d is 0.05 whole to the power of 4 by 64 into pi. The formula is I is equals to 0.307 into 10 to the power of minus 6. By substituting all this value, we get at the frequency as 49.85 Hz. Then one more condition is there, that the natural frequency of the free transverse vibration of a free shaft at different loads. The loads is of different. Different means with various positions. So let us consider a shaft AB of negligible mass which is loaded with the point loads W1, W2, W3, W4. The weights with masses as M1, M2, M3, M4. Therefore, the natural frequency for this case will be solved in the two methods. One is Rayleigh's method, second one is Dunkley's method. So this is very important techniques for getting the natural frequency for free transverse vibrations when the shaft is subjected to number of point loads. So let us consider the deflections as by applying W1 load, we are getting, if you see in the diagram, by applying W1 load, we are getting a deflection as Y1. For W2, we are getting Y2. In the same way, W3, W4 or Y3, Y4 be the total deflections under the loads W1, W2, W3, W4. We know that the potential energy P of mgh, this is the formula, mgh for potential energy, mgh. So half into m means weight, mg, m1 g1 into height is nothing but here the deflection. The deflection is how much for a single point load, y1 plus 1 by 2 m2 g2 into y2. Like that, how many number of loads is applied and the corresponding deflections or get it. So finally that is the relation we found, that is half into sigma of mg h, that is sigma of mg y. In the same way, kinetic energy, and the kinetic energy is half m v square, half mv square. Here half m1 omega y1 square, that is v of m omega y1 square. Omega means circular frequency. Omega means the circular frequency. In this case, we get it the formula as 1 by 2 into omega square into m omega y square. By equating these two terms, 1 by 2 omega square sigma my square equal to 1 by 2 sigma mg y. Half of gets cancelled. And omega square is equals to sigma mgy by sigma my square. G is constant for all. So the masses may vary, accordingly the deflections also may vary. So don't think otherwise. The G for all the masses is same, that is gravitation. G is 9.81 only. So we are keeping aside at omega is equals to square root of G into sigma of my by sigma of my square. The natural frequency is omega by 2 pi. That is 2 pi by omega, that is time period, reciprocal of time period. So with that, omega by 2 pi is equals to 1 by 2 pi into the square root of G into sigma my by sigma my square. This is the formula for natural frequency under of true transverse vibration under point load at different masses. Then by applying of Dunkley's method, next method is Dunkley's. By Dunkley's, the natural frequency of Dunkley's vibration for a shaft carrying a number of point loads under UDL condition is obtained from Dunkley's empirical formula. According to that, 1 by Fn square, that is frequency, inverse of frequency square is equals to the summation of the remaining frequencies which are developed. So accordingly, Fn is the natural frequency of transverse vibration of the shaft which is carrying point loads at UDL. In the same way, F11, Fn2, Fn3, the corresponding natural frequencies of transverse vibration of each point load. So if we applying at UDL and with different masses or weights, accordingly the deflections also will be there, the static deflections due to the loads W1, W2, W3 and so on. By taking into the account delta S is the static deflection due to UDL or due to the mass of the shaft. Therefore, we know for the mass, the natural frequency of transverse vibration as 0.4985 by square root of delta 1, 2, 3. In the same way, for all the values we have calculated, by substituting all these, we get it. The natural frequency due to the UDL or weight of the mass or weight of the shaft 0.5615 by square root of delta S. By substituting all these values in the equation, we get it the frequency as Fn is equals to 0.4985 by square root of delta 1 plus delta 2 plus delta 3 and so on, delta S by 1.21. So these delta S by 1.21 is only applicable for the UDL. If the UDL is presented, delta S is there. If no UDL is presented, delta S as 0. So we can remember that Fn is equals to 0.4985 by delta. For how many number of loads with the deflection is presented, 0.4985 by square root of delta 1 plus delta 2 plus delta 3 plus and so on will be there until the n number of. But if the UDL is presented, there we need to show delta S by 1.21. And at the same time, The delta is calculated for a simple supported shaft. That is, delta is equals to W A square B square by 3EIL. This is the static deflection formula for simply supported shaft. So with that, the Dunkley's method and Raleigh's method was completed. So finally, in the today's class, what are the applications or what are the situations that are arised due to the vibration, that is longitudinal vibrations and transverse vibrations. And in this class, the transverse vibrations, what we are considering for the frequency under point loads or uh, at different point loads. So there we are calculating the formula also, that is 0.4985 by square root of delta, and the delta deflection is the main criteria for different loads and at the same time different beams or shafts. So in the next class we will solve the some of the problems.